So now we are going to discuss the concept of moment of inertia. So we are going to start our discussion with an experiment. So assume that you have got a rod, let's say a pin, and you try to rotate this rod with respect to this particular axis, which is perpendicular to the length of the rod and passing through its center. Now, what we would do is, instead of rotating it with an axis which is perpendicular to the length of the rod, you try to rotate this rod with respect to an axis which is along the length of the rod and passing through its center, as shown in this figure. Now, I would like you guys to compare the effort you need from your side to rotate this rod. I would like you guys to figure out which of the particular cases requires least effort from your side. If you analyze these two particular situations, you are going to realize that this particular case requires much less effort from your side to rotate the rod. This is much more easier to rotate. Now, one thing to note here is, in both these cases, you are having the same rod, so the mass of the rod is not changing. What is changing is the axis of rotation. If you are just changing the axis of rotation, you're going to find out that the effort you need to provide from your side to rotate the rod, it changes drastically. Now, think about this particular scenario. Think that instead of a rod, you have a spherical ball. Now, I would like you guys to rotate the spherical ball with respect to this axis first. Again, you rotate it with respect to this axis. And again, you rotate it with respect to this axis. In this particular case, you are going to figure out that in all the three mentioned cases, the amount of effort that you need to put in to rotate the spherical balls is the same. So in these cases also, we are changing the axis of rotation, but the effort we need to put in from our side to rotate the spherical ball remains the same. So isn't it quite strange that if we just change the axis of rotation, in one case the effort we need to put in from our side to rotate an object changes drastically, and in one case it remains unaltered? If we just think deeply, we can see that in this particular case, when we are changing the axis of rotation, the distribution of mass with respect to this axis and the distribution of mass with respect to this axis is quite different. But you can see in this particular case that the distribution of mass with respect to all these three axes are identical. So let's jot down our observations. What we have observed that for rotational motion of a body with respect to a particular axis of rotation, the inertial property of the body, that is the resistance offered by the body towards changing the state of motion, not only depends on the mass of the body but also on the distribution of mass about the axis of rotation. So we can define a concept to take care of the inertial property of a body in rotational motion, and we quantitatively call that concept which defines the inertial property of a body in rotational motion as moment of inertia. So in rotational motion, we quantify the inertial property of a body by the concept of moment of inertia. So let us jot down what we have discussed till now. So in translational motion, the inertial property of a body is taken care by its mass. But when we talk about rotational motion, the inertial property of a body is taken care both by the mass of the body as well as the distribution of mass with respect to the axis of rotation. And we define a quantity called as moment of inertia, which is denoted by the symbol I, to mathematically take care of this particular property. So now let us discuss how do we define moment of inertia for a point mass. So in this case, we have a point mass of mass m, which is located at a distance, radial distance r, from the axis of rotation as shown in this figure. So in this case, the moment of inertia I of this body is simply given as mr square, that is the product of mass and the square of the radial distance. So if we have 2 point masses which are located at radial distances r1 and r2 from the axis of rotation, the moment of inertia of the system would be simply m1 r1 square and m2 r1 r2 square. That is the sum of the individual moment of inertia of the point masses with respect to this particular axis. So if we have 3 point masses it at radial distances r1, r2 and at 3, the moment of inertia would be simply m1 r1 square plus m2 r2 square plus m3 r3 square. Now we can generalize this particular property that if we have n point masses which are located at radial distances r1, r2, r3, let's say rn, so the moment of inertia would be simply given as m1 r1 square plus m2 r2 square plus m3 r3 square plus mn rn square. So we can write this particular expression by the summation symbol, that the net moment of inertia can be given as summation of mi ri square, where I varies from 1 to n. So this particular formula is valid for a discrete mass system where we have n distinct point masses located at different radial distances from the axis of rotation. But what happens in realistic scenario? In realistic scenario, we are given with bodies. So in a realistic scenario where we are given with a particular body, we can clearly see that it is not a point mass, it is rather a continuous mass system. So how can we analyze this particular scenario? So here we are going to assume that this particular body is made up of a large collection of point masses. To be precise, let us assume that this particular body is made up of infinite number of discrete point masses so that there is no void in between. And by adding all the point masses and placing them at different radial distances, we generate this particular body. And we call these types of bodies as a continuous mass system. So what do we have here? We call this as a discrete mass system and we call this as a continuous mass system. Now let's try to see how do we define moment of inertia of a extended body in rotational motion. That is, how do we define the moment of inertia of a continuous mass system? So as I have mentioned just now, that a continuous mass system is nothing but a collection of infinitely large number of discrete point masses. So let us assume that we have a particular point mass of mass, let's say dm, which is located at a distance r from the axis of rotation. So moment of inertia of this particular point mass of mass dm can be written as dm r square. So the total moment of inertia of the whole body can be written as integral of the moment of inertia of all these elemental point masses. So it can be written as integral of di, which is integral of dm r square. So in case of discrete point masses, what do we got? What have we derived? The moment of inertia is simply given as summation of mi ri square, where I varies from 1 to n. And for continuous mass systems, the moment of inertia is simply given as integral of dm r square. Now I would like to also point to another salient feature. Just try to observe that if we are calculating the moment of inertia with respect to a particular axis, which is this, we are writing di as dm r square. Now just imagine if we simply try to calculate the moment of inertia with respect to, say, this particular axis. So in this case we have to take the radial distance of the point mass with respect to this particular axis. Let's say this as r prime. So in this case the moment of inertia of this elemental point mass would be dm r prime square. So in this case, the moment of inertia I prime, let's call this I prime, which is with respect to this red axis, would be integral of dm r prime square. So clearly I prime is not the same as I. So clearly moment of inertia for the same body depends on the location of the axis of rotation. So whenever we are talking about the moment of inertia for a particular body, we also need to specify that with respect to which particular axis we are going to calculate the moment of inertia. Let's say we have a particular body like this. The moment of inertia for this body with respect to this axis is going to be different, with respect to another axis is going to be different. So we should always be careful about which particular axis which are we considering for the calculation of moment of inertia. Now let us try to calculate the moment of inertia of a ring, and we are gonna assume that the ring has a uniform mass distribution, and let us try to calculate the moment of inertia of this particular ring with respect to an axis which is passing through the center of the ring. Let us assume that the ring has a total mass of m and it has a radius of r. So by uniform mass distribution, I simply mean that if you consider a particular length, let's say L, in the ring, and the mass in that particular segment is m, if you consider another segment in the ring of same length, you're going to get the same mass. So the mass is uniformly distributed on the length of the ring. So let's try to calculate the moment of inertia of this particular ring. So here in this case, what we can do is we can try to consider a small elemental mass dm which is located on this ring. So clearly this elemental mass is located at a distance r. So what can be the moment of inertia of this elemental mass? This is going to be dm times r square. So what is going to be the total moment of inertia of this ring? It is going to be simply integration of di. So what can we write? Dm times r square. Now what we can see is that for all the elements in the ring, all these elements are located at the same radial distance from the axis of rotation. So the radial distance for all the elements is constant. So we can take r square out of the integral. So we get the moment of inertia as r square times integral of dm. Now what is integral of dm? Integral of dm is simply the total mass of the ring. So what do we get? We get the moment of inertia of the ring as r square times m. So what is the moment of inertia of a ring? The moment of inertia of a ring with respect to the central axis of rotation is mr square, where m is the total mass of the ring and r is the radius of the ring. What have we assumed here? We have assumed that there is a uniform mass distribution along the ring. Now let us try to calculate the moment of inertia of a disk. Again, for this disk, we are going to assume a uniform mass distribution. That is, mass is distributed uniformly along the surface of the disk. So if we consider any particular area of this disk, and let's say of area A, and if we consider the same area A somewhere else on this disk, both are gonna have the same amount of mass. So now let's try to calculate the moment of inertia of this particular disk with respect to an axis of rotation which is passing through the center of the disk. Now what are we gonna do here is we are gonna exploit the result that we just derived in the previous case. So on the figure, in this figure, I'm simply showing you the top view of the disk, where this point is nothing but the axis of rotation of this disk. So what I'm doing is, at a distance x, I'm considering a thin ring of thickness dx. So what is the mass of this particular ring? let's say dm. So let us assume that this disk is having uh, a total mass of m. So what can be dm? So if the total mass of the disk is m, what is the surface mass density of this particular disk? It would be m by pi r square. So this is the amount of mass which is there per unit area in this particular disk. So what is the amount of mass which is there in this particular ring? It should be equal to m by pi r square times the total area of this particular ring, which is nothing but 2 pi x times dx. So what do we get? 2mx dx by r square. So what is the moment of inertia of this particular ring? The moment of inertia of this particular ring is dm times x square. So let us simplify this equation. So it is 2mx dx by r square times x square. So it is 2m by r square x cube dx. So what is the total moment of inertia of this particular disk? It would be integral of di. So what we can write? It is simply integral of 2m by r square x cube dx. So what do we get? It's 2m by r square integral of x cube dx. Now what are the limits for x? So we are going to consider rings from the center of the disk to a radial distance of r. So x varies from 0 to r. So we are going to get 2m by r square into x to the power 4 by 4, and x varies from 0 to r. So we get it as 2m by r square to r to the power 4 by 4. So finally we obtain I as m r square by 2, where m is the total mass of the disk. So let us jot down the results that we have obtained. So for a ring, with respect to the axis of rotation passing through the center of the ring, we obtain the moment of inertia as mr square, and for a disk we obtain the moment of inertia as mr square by 2. So clearly what we see that the moment of inertia for a ring is greater than the moment of inertia of the disk of same mass as that of the ring. So if we have a ring of mass m and if we consider a disk of same mass, the moment of inertia of the ring is going to be greater than the moment of inertia of the disk. Now let's try to physically understand why is it happening. So let us imagine that we have a ring as shown in this figure, and let's try to understand how do we generate a disk from this particular ring. So here we are given with a ring of mass m and radius r. So if we want to generate a ring from this a disk from this particular ring, what we need to do is instead of all the mass lying at this particular radial distance r, we need to spread this mass throughout this region. That is, we need to bring all these masses which are located at this radial distance nearer to the center of the ring. So we have done the same in this case. What we have done here is, instead of all the mass being concentrated at the radius of the ring, we have brought all the mass completely spread around this region which was earlier completely empty. So effectively what we have done is we brought some mass located at the radial distance from the center to closer distances. So earlier all these masses were located at the radial distance, which was the maximum distance from the center, and effectively we have brought some of the mass closer to the center of the ring or closer to the axis of rotation of the ring. So clearly, if we just call the moment of inertia of a particular element as dm r square, initially for this particular ring all the elements were having a moment of inertia of dm r square. Now we are converting it for some of the elements, we are writing it to be dm r square, where r square is less than r. So effectively that reduces the moment of inertia of this particular disk. So that is the reason why the moment of inertia of a disk is less than the moment of inertia of a ring of same mass and radius.